All right, so welcome back to this video. So in the last video, I have explained you the YOLO V1 algorithm, the version one of YOLO algorithm. This is like the most used object detection algorithm. I'm just going to first recap what is YOLO one V1 algorithm. So what I have told you is, let's say there is an image. Sorry. So let's say there is an image. Okay, is that? So there is an image, right? So there is an image, and let's say this is our object. Let's say this is our target object, and then what we'll do is we'll just split this um, image into constant sized um, uh, like grid cells. So we're going to use some grid cells. In the paper, they have used 7 by 7 grid cells. We have, let's say we have 7 by 7 grid cells. We'll just divide that image into 7 by 7 grid cells, and what we'll do is we'll just create a matrix or create a vector. Yeah, create a matrix of all these values and input all of these grid cells to a CNN. I told you that we'll input all of these values to a CNN. Let's say we will input all of these grid cells, matrix of matrices, and then we'll perform the CNN operation, and we'll for each, and then what we're going to do is we're going to get the like the object, right? So where each grid cell we are going to predict a, so output is going to be a matrix. So this matrix contains of what does this matrix contain is, in this matrix we are going to get these x, y, w, and h values. So what is x, y values? So for every object we are going to get a midpoint. So for example, this cell contains the midpoint of this object. So the cell is responsible for getting this midpoint. Others x and y doesn't matter. And then each grid cell in which the confidence score is high. Let's say this grid cell believes that it has the object, for example, then this is going to predict a bounding box. So all of these are going to predict a bounding box, and then finally we are going to use non-max suppression to get the final bounding boxes. Because we are going to get many number of bounding boxes, right? So first, after that, we are going to do non-max suppression to get the final bounding box. Hence, we can find the bounding box. We can generalize this to multiple objects, because as we are performing independently for each grid cell, we can it easily can be generalized to two or many objects and classes. Right, so that is what I've told you about YOLO V1. We're going to have these midpoints and all that. So now, in this video, we are going to cover some things. We are going to cover some new things. First I'm going to right. First, I'm going to cover the new YOLO V3 algorithm. Right, YOLO V3. So what is YOLO V3 is, there is not much number of changes. There is no like huge changes, but there are just slight changes. So the main change is in the architecture. So we have the CNN architecture, right? So in YOLO V3 we had residual type networks. So we have two types of residual connections. I have already told you about residual networks in the one of the past videos on resonets. Make sure to watch that. So what is resonate is, in order to solve the problem of vanishing gradients, in order to give more importance to little features inside, let's say, an image, we are going to have this gradients. So we are going to have this gradients of the earlier layers to add. So we are going to add the gradients of the earlier layers to the um, to the final layers, right? So that is the idea of resonate. So what are we going to do is, not only that, we are not only going to do this, we are also going to concatenate these values. So we are going to concatenate these gradients of the or output of this layers with the outputs of the later layers. So that is a change in architecture. And also another huge change is that, let's say we have our architecture of CNN layers. So these are all layers. So what we had is, I'll just explain you what it is. So rather than using, let's say we have, uh, let me just introduce you to a problem before this. What first, in order to understand these networks, first you have to understand why they use this network, right? So the problem of using this network is, let's say you have an image. Let's say you have a very small target object. Right, so you have very let's say there is a car in a very far distant space. You don't want then you don't want to use very huge um, boxes, right? So you might mind to you might miss them. So therefore, we have to use specific size of grid cells. So you have to, like, you can't use a specific size of grid cells, right? So um, in order to generalize for both smaller and larger objects, this architecture will help. So let's say while detecting objects, there can be larger cars that can cover almost all the frame, and there can be very smaller cars in the very distant space. Therefore, in order to solve this problem, this architecture was built, in which we had like different scaled predictions. Let's say we have one scaled prediction here, in which let's say they use 16 by 16 grids rather than, let's say, 7 by 7 grids. They use 16 by 16 grids, and they would just upsample this and then carry out this to the network, and then would have another, let's say, 32 by 32. I don't remember the actual numbers of these grid cells, but we had, rather than using a constant 7 by 7, we had this uh, sample outputs of 16 by 16, 30 by 30, 32 by 32, and also 50, I think 52 or something. So in two, like by having this architecture, we can therefore generalize to both larger and smaller objects. So that is what I have proposed in this paper. So this is the paper of YoloV3, and then let's just look at this. Oh yeah. So as I told you, there are residual connections, right? This network is called Darknet 53, by the way. And then yeah, so that is the paper. You can also read it. I'll put it in the description. Another new thing, I think it is introduced in YoloV2. So I am not covering YoloV2 because it is not actually that important, right? YoloV3, another new thing is, rather than predicting the x, y, w, and h for each grid cell, sorry, so rather than predicting this x, y, w, and h for each grid cell, what we are going to do is, for each grid, we are going to have a bounding box. We are going to have a bounding box which is, let's say, average, or like just an average bounding box. That doesn't mean anything. So we are going to train the model such that it can update this anchor box. So this is actually called the anchor box. And then we are going to update this anchor box such that we could come with anchor boxes that are better. So we are going to update these anchor boxes such that they're better. So this is the YoloV3 architecture. Just try to read about it if you want. If you are interested in computer vision, if you are really interested in object detection, I'll also I think I'll also I'll provide you with some resources in the description. So make sure to check that out. We have this amazing paper uh, about all these experimentation they did and all that. So make sure to check that out too. And in this video, and then in the next part of this video, so what we are going to do is, we are going to develop a YOLO architecture. We are going to actually solve a problem of YOLO by using the pre-trained YOLO model. So we will be using YOLO version 5. So there are many versions of YOLO. Currently, version 8 is the latest one. In this project, we are going to use YOLO version 5, which is very powerful. We are going to use this YOLO version to solve a problem of car detection. So YoloV5, it's actually pre-trained. It's already trained. So what we'll do is, we'll just get the weights of this YOLO architecture, and then we're going to use this to predict on car data set. So actually, YOLO is trained on a like huge data set. I think it is trained on something like Coco data set or Pascal data set, right? So this data set has many classes. So they like cars, human faces, and all that. So they'll just train it on this huge data sets, and we can use these image classifier models that are trained on these data sets to accomplish our works. So I'll just go through this code very fastly. What this is. So first, the problem that we are solving in this thing is car detection. We are going to detect cars by using this YoloV5. So we are going to detect whether there is a car in a specific object. So yeah, we are going to draw a bounding box if there is a car in a specific frame. First, we are going to import the necessary libraries, torch, numpy, pandas, and all that. And then after that, there is the actual, so YoloV5 was developed by a company called, I think, Ultralytics. So it is Ultralytics. They will just have this GitHub directory of some of all the models, right? It is a very clean directory almost. So you can just go through all these folders, and they have developed YoloV5 in this GitHub directory. GitHub is a place where you can store these models, right? So this is actually the YAML files are the are the trained model files. So whenever you train a model, let's say any type of model, you can save this model. You can save this training model, precisely the weights of this model, and then you can just save this weights of the model and use it to solve problems, right? So you can, if you let's say you train the model to detect cars. So in order for you to use it on actually detecting cars on, let's say, for a website, you can just download these files into a YAML format, right? So you can download this in a YAML format. I think there is another format. That format is H1 format. Yeah, you can also download model on H1 format or YAML format, and you can just use this trained model files. These are just outputs of the trained model. You can just use the trained model to predict on new thing. To be precise, they just store the weights of this model. As you can see here, we will git clone the this directory. So this is a GitHub link. So this is a GitHub link. You can just put it here and type git clone. Right, I'm using exclamatory mark because this is not Python. This is just command on command prompt. You might have used the terminal or command prompt on your computer. So these are all instructions for your command prompt, for the environment. And then we'll import the necessary repositories and install some necessary dependencies. So requirement doc text is nothing but the requirements for this YoloV5 algorithms to run. And then we'll do the same object detect, like pre-processing, center YWH classes and all that. And then we already have this data from Kaggle. This is the data folder, right? I'll provide you with the problem in this description. You can just go and maybe just download the data or something. Yes, you can just look through some images using this. Yeah, you can just randomly pick, let's say, a car image, and then just go through this training data set and all that. So you can just check that out. And after we done the pre-processing, it is actually very easy, right? Just that. Yeah. So this is the command. This is the little command to use the pre-trained YoloV5. So here we are using YoloV5 S. S means small, right? So as the problem is not very bigger, we'll just use a small model. The small model has lesser parameters or lesser weights than the larger and medium model. So we'll just use these weights of this model to predict on the testing data set. So we don't even have to worry about the training of the model, because the model is already trained on a very huge data set called probably Coco or Pascal data set. No matter, doesn't matter. So the model is already pre-trained, so we can just use this pre-trained model to detect our specific classes. And then if you can just run it. You can just when we just run it, we can just save these files. We can just save the outputs to this new folder, work YoloV5 slash runs, let's run slash detect slash exp. So we just store the predicted files in this xp. So no, we are not going to predict it. So this is the output of this directory, so or this specific function, right? So after we run this specific file, or run this specific run this specific repository, I should say, we'll get this output. We are going to show this output into this little folder, right? I'm going to run this. If you run it, you can see that this is the training image, and this little box is predicted by the YOLO model. And as you can see, it is actually pretty accurate. There is no car here, so it doesn't predict anything. And then there is no car here, no car here, no car here, no car, and it actually predicts it with a decent confidence score also, 80%, 74%. And yeah, look at this, like it is able to predict thing. I think, is it a car? Maybe, maybe not. it's able to detect it's actually not a person, but it thinks it is a person because the model is trained on a very large data set of many things. Yeah, it can able to detect traffic light with very good confidence score, and also cars. Like, that's wonderful. So yeah, this is how you can use pre-trained YOLO V5. So YOLO, these are like, that is a good thing about this current age. Like, if you want to get into AI and machine learning, there are a lot of powerful machine learning models that are already pre-trained. You can actually use this use those machine learning models to do some epic things, right? So thank you for watching, and I'll see you in the next video.